In this part of the chapter, you're going to learn about vapor pressure and subsequently the boiling points of liquids. What happens if you spill water and not wipe it off? It eventually evaporates, disappears. It escapes into the gas phase. It's a conversion from a liquid to a gas. Evaporation happens at all temperatures, even at room temperature well below the boiling point of water. Evaporation is also a surface phenomena. It occurs only at the surface of a liquid. The molecules at the surface are the ones that can escape. So if a molecule at the surface has enough kinetic energy, it can break free from the intermolecular forces that keep it with the rest of the liquid molecules and escape into the gas phase. And if the container is open, the gas particles can get away from the surface. More and more particles evaporate, and eventually all the liquid evaporates and all is converted to gas phase. If you put a liquid into a closed container, evaporation of course will happen, but in this case the liquid is not going to dry off because the gas molecules cannot be carried away and they build up in the space. As they build up in the space, they're going to start condensing. The molecules, as they zip around, when they collide with the surface of the liquid, can be captured. That process is called condensation, going from the gas phase to the liquid phase. At some point, there will be enough gas molecules such that the rate of condensation will catch up with the rate of evaporation. The liquid evaporates at the same rate the gas condenses. This is what we call a dynamic equilibrium, where the rate of evaporation from liquid to gas is equal to the rate of condensation from gas to liquid. The evaporation and condensation processes do not stop. They continue to happen, but they are happening at the same rate. This is why we call it a dynamic equilibrium. At that equilibrium state, the amount of gas molecules is constant from that point on. Therefore, pressure from that point on is constant. This is what we call the vapor pressure. Vapor pressure is the partial pressure of the vapor of a liquid measured at equilibrium at a given temperature. The vapor is above the liquid. Vapor pressure depends on several factors, one of which is the type of the liquid. If you compare ether, ethanol, and water, let's say at 35 degrees Celsius, you see that water has the lowest vapor pressure and ether has the highest vapor pressure. If you look at the pictures of balloons attached to flasks containing water and ether at 35 degrees Celsius, the flask with the ether has the balloon filled with gas because of ether's higher vapor pressure at that temperature. Ether evaporates more easily than water. It is more volatile than water. We call higher vapor pressure liquids to be volatile liquids. They evaporate more easily. They evaporate faster. If you look at the dependency of vapor pressure on temperature, you also see that vapor pressure increases exponentially with increasing temperature. If you compare the vapor pressure of ether at 0 degrees Celsius and 35 degrees Celsius, there's a dramatic increase. You can see that from the inflated balloon at the higher temperature. So those are the two factors that affect vapor pressure: the type of the liquid, but more so the temperature for a given liquid. We established the fact that, by observation, ether is a more volatile liquid than water. It has a higher vapor pressure at a given temperature. But why so? To explain that, we need to look at the intermolecular forces that are present in the two liquids. For that purpose, we need their Lewis structures drawn, which will reveal what kind of intermolecular forces each can make. Water can make hydrogen bonds. But ether cannot make hydrogen bonds, has only dipole-dipole attractions. Hydrogen bonding in water is a much stronger intermolecular force than the dipole-dipole attractions observed in ether. This means that stronger attractive forces result in a lower vapor pressure, and vice versa. Weaker attractive forces would result in a higher vapor pressure, as in the case of ether having a higher vapor pressure than water. Because the intermolecular forces are weaker in ether, they are easier to break, and ether will have a higher tendency to evaporate, thereby having a higher vapor pressure because of its weaker intermolecular forces. Let's use the vapor pressure curves for one other purpose. We're going to focus on water, and as you can see, the vapor pressure is increasing as temperature is increasing. For the vapor pressure to be 760 millimeters mercury, water has to be heated up to 100 degrees Celsius. What is 100 degrees Celsius for water? It's its boiling point. So what does that tell you? When water is heated to 100 degrees Celsius, its vapor pressure becomes equal to the atmospheric pressure. And this is the temperature at which water starts to boil. So boiling point is the temperature at which the vapor pressure is equal to the external pressure. For water, the external pressure has to be 1 atmosphere for its boiling point to be 100. This is the point where bubbles form within the liquid. This is different than evaporation, which happens only at the surface. Boiling happens within the liquid. Bubbles form within the liquid and go upwards. You can think of it as a battle between atmospheric pressure, which pushes the liquid down, keeps it as a liquid, and vapor pressure, which is the upward pressure trying to fight against it. Only when the vapor pressure is equal to the atmospheric pressure, it can push against the atmospheric pressure and the water or the liquid boils. 100 degrees Celsius for water is known as its normal boiling point. Normal boiling point is the boiling point at 1 atmosphere pressure. Boiling point depends on external pressure. For water, the boiling point is 100 degrees Celsius only if the external pressure is 760 millimeters mercury, or 1 atmosphere pressure. If the external pressure is lowered, then boiling point will also be lowered. If the external pressure was 600 millimeters mercury, then the boiling point of water would be less than 100 degrees Celsius. At sea level, atmospheric pressure is 1 atmosphere. Therefore, water boils at 100 degrees Celsius. But if you increase your altitude, if you climb the top of a mountain, the air gets thinner, air pressure gets lower. At the top of Mount McKinley, the approximate pressure is 0.46 atmospheres. At this pressure, water boils at about 83 degrees Celsius. This is the maximum temperature you can reach with liquid water, because at that temperature it will start boiling. This is why cooking food at the top of a mountain requires longer than cooking the same food at sea level, because temperature is lower. When the temperature is lower, you need to cook for a longer period of time. Conversely, when you use a pressure cooker, the pressure inside the cooker is larger than 1 atmosphere pressure, and the boiling point of water increases. You can reach a higher temperature as liquid water, and therefore cooking process takes shorter amount of time. Because intermolecular forces affect vapor pressure, they also affect boiling point. If you look at the list of organic compounds called alkanes with increasing number of carbon atoms, as a molecule gets bigger, the London forces observed will get stronger. And look at the boiling points of the series. As the molecules get bigger, as the intermolecular forces increase, boiling points also increase, which means that stronger attractive forces result in higher boiling points, or vice versa. Weaker attractive forces would result in lower boiling points. So let's go over how the liquid properties that we have discussed are affected by the intermolecular forces. The stronger the intermolecular forces, the higher the surface tension of the liquid will be. Likewise, the higher the viscosity. Although viscosity also depends on molecular shape, which affects entanglement. Entanglement slows the molecules down and increases viscosity. Stronger intermolecular forces also mean lower vapor pressure, which corresponds to a higher boiling point. The strength of the intermolecular forces also affect enthalpy of vaporization. Enthalpy of vaporization is the energy required to vaporize 1 mole of liquid at its boiling point. We are going to discuss this term later on.